loud. All right, so today we're going to kind of go the opposite direction that I've been going before, right? So we introduced the gates in the beginning, and then I went ahead and kind of abstracted up into talking about block diagrams, right? Where we can use like multiple AND gates to build multiple 2-input AND gates to build a 4-input AND gate. In your homework, the homework 3 that I'm sure all of you have definitely started, there's a homework assignment to build a 4-input OR gate using 2-input OR gates, right? And we can build this up in what we call a hierarchical structure where we use little blocks to build bigger blocks. But today we're going to go the other direction. We're going to go peek inside of how do we make AND gates? What are AND gates, OR gates, etc. made from? Now, there's further layers to what we're going to talk about. We're not going to get down into what we reference as device physics, which is how do semiconductor materials work from a physics standpoint. We're just going to learn a different way to draw pictures of what we call transistors. Who here knows what a transistor is? Nobody, right? Great, cool. We'll start from nothing then, which is to be expected, I guess. So transistors are the things that enabled the whole world that you know and love now. Transistors are devices that respond to electrical input very quickly, right? And we're going to learn about how to use transistors as digital devices. Transistors are part of the real world, right? Which means they are analog devices because the real world is analog. But it turns out we can pretend like they're digital as long as we set them up correctly, okay? And so we built circuits, digital inputs, right? Just using a resistor, and we can throw a switch. But those resistors are big. And it turns out no matter what we do, when you get down to kind of micro scale or nano scale devices, which is what's in your phones and tablets and PCs, right? Big resistors are bad. We can't do things quickly because the bigger they are, the slower they go. And so what we want is a device that functions as a switch. And that's what a transistor does when we start considering it as a digital device. And we're just going to draw them like so. Let's start over here, I guess. Okay, that's all a transistor is in drawing. And basically what happens is we call this the gate, okay? There's 3 terminals on this. There's the gate, the source, the drain. I don't really need you to memorize which is which, other than you're going to hear me talk about the gate a lot. When you get into your junior level courses, ECE 3110, they're going to be a whole lot about the source and the drain behavior when the voltages are different between the source and the drain. But I'm not going to overwhelm you. This is a freshman level digital circuits course. So let's just focus on what happens to the transistor when I put a voltage at its gate. The gate is its input. It's the thing that tells the switch whether it is on or off. And so what it wants to happen basically, it is if the gate is 1, then current can flow through it from your sources and your drains, from the other 2 nodes, right? Let me see, actually, I'll see if I can make the projector happy in just a second. Oh, wait, it's hooked up to this computer. Yeah, I guess I'm not gonna struggle with that. So source, drain, right? We'll just call it. Again, I don't expect you guys to memorize that, but I guess I realize now as I start talking, it'll help with just the vocabulary of it, right? Anyways, if the gate is on, you can go from the source to the drain. Current flows, yay, we're happy. If there's a 0 there, it turns off. So basically, this device looks like a switch, but it has a button on it that we can push to close it, right? You could imagine that this is pushing down and closing it if you've applied pressure. One, right, voltage is the physical water equivalent of pressure, right? Higher voltage, higher pressure. I give it pressure, it pushes in, it closes the switch, and it's on. Everything flows. Turns out we can have another device. This is called NMOS, and that's because MOS is the type of transistor that we're using. Metal oxide. That's all the MO stands for. Then the N just means, well, you'll get into more later, but we reference it as N type, and all that's telling us is that a 1 closes it. There's another type of gate. The type of transistor looks like that. Little bubble, we're familiar with it by now, right? That means that a 1 is open and a 0 is closed. It just inverts what the function is, right? This is called Cmos. These two devices function as the beating heart of all things electronic, all things high-speed electronic, digital especially, right? There are other types of transistors. We don't need to know them yet. You will learn them later. These are two, and when we stick them together, when we take an NMOS and a PMOS and we stick them together in an intelligent way, we get CMOS. The C being complementary, meaning they work together, okay? And why do we care that they're complementary? Well, let's go ahead and build the circuit that we did. Oh, I'm going to specify, just because I am very abstracting the material for this class because there are so much that could be known and discussed about this. This is such a simplified drawing of how we would normally use an NMOS device that we could consider it wrong almost. But I don't want to overburden with you that. So when you get to further classes and be like, well, Dr. Gardner never drew it that way, just be aware I'm doing it on purpose because I don't want more detail than is necessary, because what we want is an understanding of how the devices work from a high level standpoint. We want you to know what's inside of them, but we're going to save the nitty gritty details for later. So let's just be aware that I'm way oversimplifying what's happening with these devices, okay? All right, well, we know this is a switch. I can put a resistor up to VCC, take the output. If I put in input voltage or some digital signal, if I put, say this is a 5-volt CMOS, that's allowed. They can have 5-volt CMOS devices. They can, it could also be a 1.8 or a 0.7 volt, or it could be smaller. But then we put ground here. And what happens is, if I put a 1 on this device, on this switch, it closes, right? Kind of, you imagine this is the plate and you put a 1 and it pushes down and now it's a complete switch. The current can flow. That means this node, I'm going to call it V out, the voltage output, is ground, right? Because if the switch is closed, this is connected directly to ground, 0 volts. If I put a 0 here, the switch is open, there's no path to ground, the resistor pulls it up, and I get a 1, right? So that means a 1 makes a 0, 0 makes a 1. I build a transistor, or an inverter, right? This is the same kind of thing that you built with your switches. It's just replacing the physical switch that you're going to go throw the buttons on with a conceptual device that is so tiny that you can't really see it, right? Your modern devices in like your cell phones and such are 14 nanometers or smaller very often. They are very, very tiny transistors. And that means they can go fast. The faster they are, the smaller they are, the faster they go. But I already said this resistor, this works, right? But the resistor is big. Resistors are big compared to MOS devices. It's not ideal. So we're going to take advantage of the PMOS complement situation build this circuit. Well, now let's look at what happens. If I put a 0 in, I'm going to take the VI equals 0 case. Well, that means that the NMOS, we've already established what happens to the NMOS. If I put a 0, the 0 means it's open. So on the bottom side, I have an open switch. Well, now there's an inverter. So on the top, right, that's what the PMOS little bubble says, is that it just behaves opposite of the NMOS, which means that my switch is closed. Now I built this circuit where VI, VO. Okay, well, let's look at the VI equals 1 case. And I don't mean 1 volt, right? I mean whatever the VCC is. Right, the supply voltage tells me what 1 equals. So in this case, let's pretend VC is 5 volt. That means VI is 5 volts. But this is 1 on true, right? That connection. Well, all I end up with is the opposite scenario. Here. Okay. Well, this case, we're not connected to ground, right? The switch is open, it can't see ground, therefore not ground. But we are connected directly to VCC or on. So the output in the VN is 0, VO is 1. This is an inverter, right? Because here, if VN is 1, then that closes the CMOS, connects it to 0, or sorry, the NMOS, and then opens up the PMOS. We build an inverter. No more resistor, no big bulky components. Now both of those devices can be 7 nanometers in each dimension, and it's super tiny, right? And now we can put a bunch of them into your cell phone, and your cell phone can go really fast, and we're happy with our modern technology. There's another benefit to this type of architecture over this one. Does anyone see what it is? Okay, if you don't, I want to make it puzzle for a minute.
No resistor.
Yeah, there's no resistor, and that makes it smaller. But what else does removing the resistor do? Not quite. Good thought. It's kind of the same number of components, but what it does is when this switch is sorry, I just trapped you up. There was a trick question I messed up. Compared to like our fine. Let me just rephrase this because I just confused everybody, and I'm going to start again. Okay, so something that's cool that's happened here is devices, right? Remember I talked about the Nand gates and how in an ideal world there would be no input current, but there's a little bit of leakage. Well, the devices that you have actually have really, really bad leakage current. Most of the time it's very small, and we pretend like no current flows through the gate. And also, when we look at this device, if in either of the cases, one of the switches open, there is no path between VCC and ground ever.
So there's no leakage.
Well, there's no power consumed. Because if there's no current flowing, there's no power, right? It's just like how your socket is sitting at home is just sitting open. It's not connected to anything. You're not getting charged electricity for the power that's not getting completed. There's no current, there's no power. It saves your battery. Whereas in this case, if I close the switch, the current flows through the resistor, it burns power. It doesn't burn power if I'm open, but it's burning power half of the time if if you assumed equal distribution, right? So not only does this save us area, it also saves us power other than whatever is consumed by a small amount of leakage current, which is really nice because we don't want our cell phone batteries to die faster than they need to.
I have a quick question.
Mhm.
So what are like the two dots when the transistor is going over and connecting it, like where V1 equals 0 right under the
Oh,
VCC?
these two dots?
Yeah.
Oh, I'm just showing the terminals of the switch,
Okay. Okay.
right? So that I could just draw it as the wire, but I wanted to remember that there is a switch
That is there.
here. Yeah, good question. You'll see it drawn that way sometimes for a closed switch. Just be like, oh yeah, there's a switch here. The other way that if I did this more intelligently, I guess I could have done something like that and had the arrow to show that it could open. Right? There's a couple ways to communicate that it's not just a wire; it's a switch that could open.
So
yeah.
why in the last one is it still open to ground? Like, why is it not connected all the way through?
This one,
Yes.
because VCC is here,
Yeah.
and I'm broken here. VCC doesn't have any path to ground.
Yeah, but like up, like just below V out, is it broke there? No. Yeah. That's right there.
This, let me redraw that a little bit so it's maybe a little clearer. I don't know what I did with my blue pen. Let's just remove the switch altogether.
So that okay.
Sorry.
I didn't see that.
Yeah, I erased that one
I
and
thought it
changed the
was open on
switch.
both sides.
Yeah, yeah. What would happen if it was open on both sides? We don't know, right? The voltages, we don't know. Yeah, so that's my mistake. I didn't finish redrawing it when I.
You're good. I just was confused about what was going on.
No, I'm glad you asked because if I leave you guys confused, it's not really good. Because any other questions? If I left you too confused because I got lost and things obfuscated? Okay, I apologize for that. All right, now let's go ahead and focus more on kind of what we'll call the architecture of this device. To be complementary, it needs two parts. It needs a pull-up network to make it a 1 if it wants to be true, and a pull-down network to make it 0 if the output should be false, right? And so in this case, the inverter is the most simple device in that our pull-up network is 1 PMOS and our pull-down is 1 NMOS, making a Cmos inverter. We like Cmos inverters because they're small and fast. Now, this idea is going to kind of propagate through as we go build NAND and NOR gates, which I'm just going to tell you this and you kind of have to accept it. The PMOS devices in digital logic will always go on top, and the NMOS devices will always go on the bottom, meaning PMOS wants one side connected to power, and NMOS wants one side connected to ground. Now, this comes from the deeper levels of physics that says that there needs to be a certain voltage between the gate and the, what did I call that one? Drain, right? And we have various rules, right? Gate source drain. We need to make sure that we have them in this nice equilibrium so that the device can turn on. If I put the NMOS up here, it will just never be able to turn on because device physics says so, and it's inconvenient, and you'll eventually learn about that. I believe in 3110 is where they go into it first here. So this is just memorization for us. We don't have to understand yet, right? That's kind of the first step to learning sometimes, is just memorize what has to be true, and then we'll go figure out why later. Okay, so we're going to use this idea of PMOS device and NMOS device together, building a pull-up and pull-down network to make NAND and NOR gates. And we're going to start with NAND and NOR gates because it turns out they're easier to design than AND and ORs. And we're going to kind of see why, and it's this pull-up network, which is the inverting nature, which is the PMOSs have to pull up. They can never pull down, which means if I put a 1, it's a 0, right? It sees a 0, it's not closed, and it can never pull up on a 1, right? It's just a logical consequence of the position of the PMOS device. So anytime we design a circuit that we're going to start thinking about how these work, what we want to do is look at it from the perspective of the pull up and the pull down situation. And I said we're going to start with NAND. And then we're going to, well, AND would have a 1 and the rest of zeros, so NAND is 1, 1, 1, 0. Right? This is our truth table for NAND gate. So now we can choose, should we build the pull up or the pull down network first? What is more interesting to us? Well, it turns out that the pull down is probably easier because there's only one situation in which we want to be connected to 0, right? Is if I have a 1 and a 1. So what that says is my pull down network is always NMOS. And operations, A and B, are in series. I called that NAND, so let's go ahead and call that NAND. Yeah, we're working on it. We're not really there yet. But now we can see that if A is 1 and B is 1, then both of those switches are closed and there is a direct path from the output NAND to ground, and it makes a 0. Right? Well, now I need to look at it and say, what happens if, or rather, let's do the other way. How do we make 1s? Well, we want a 1 to be true if we have 0, 0, or 0, 1, or 1, 0, right? We have this OR situation, and it's ORed from the perspective of the zeros, right? The NAND, we could say, it kind of helps to think of the NAND gate in this form of it for this part, right? Where we care about the OR input of the zeros, basically. Okay, and what that does for us, well, if A or B is 0, then I wanted to make it go 1. A 0 closes the PMOS. Well, OR operations I'm going to erase this and change the color just so it's a little easier to see the B trace. Well, now, if A is 1, this closes, and that one opens. And if B is 1, this one closes, and that one opens. So they are complementary to each other, and the only way we get a 0 is 2 1s. But if either A or B is 0, I've connected NAND to 1. Right? And if A and B are both 0, then we have 2 paths to VCC, 2 paths to 1. Doesn't really matter if 2 things connect that are the same voltage, everything's fine, right? If 2 things connect that are different voltages, I have a problem. So that's one of the things that I'm going to have you do, right? Is I've had you start by analyzing circuits, and then you started designing circuits using the abstracted gates. Well, you get to do the same thing with these, where we get to look at it, and I might give you a picture and ask you, what does this device do? And the first step is to draw out the truth table, right? And you can redraw this a bunch of times, 4 times, with the various switches closed and see what is the output connected to. But we can see I started the other way this time. I built a NAND gate using the principle of pull up and pull down networks. And the pull up and pull down have to be opposite, which means essentially that any well-designed circuit is just going to have either one of them, the pull up or pull down, is going to be in series, one after the other. And the other one is going to be parallel, side by side. That's pretty much what everything is going to fall out as. And so I built a NAND. If I want to turn this NAND into an AND, what do I do? Invert it, right? A not and is just and. So if we invert the NAND, I end up with and. So in order to build an AND, it takes me 6 gates. To build a NAND, it only takes me 4.
You won't see like have like exclusive and gates. How do you do that?
We'll get there. Yeah, we'll get there. But let's start with NOR. Let's build the NOR. And does anyone have like an intuitive way of thinking? What do you think the NOR gate's going to look like?
It's going to be in series on the top, parallel on the bottom.
Sounds reasonable, right? If we just flip the pull up and pull down from series on the bottom, parallel on the top, to parallel on the bottom, series on the top, let's see what happens, right? And so we're going to do this one the difference way, where my PMOSs are now in series. And my NMOSs are going to be in parallel. We're going to tap out between those two. We're going to call inputs A and B. A is going here and here, and then B, I'm going to use B in green again. There. Right. Either way is fine. Like, see how this VCC, I just connected them together and they both went to VCC, or I draw them as separate grounds. Both are correct, right? Because ground, just like if I use a symbolic naming, like if I call one thing A on one page and I call it A on the next page, those A's are connected together, unless they're at a different level of the hierarchical design, of course. But this ground is okay. So I could also do that. Right, same thing, just different ways of drawing it. Sorry, this was kind of bad. I try and stick to 90-degree angles, but apparently I forgot. It just makes it look a little bit nicer. Let's use our analysis skills now to see what happens. And we're going to use the truth table, right? The truth table is our friend. It turns out truth tables are really useful. I know there are 2 inputs. And now I have some function, which I can draw a question mark, well, let's just call it f. Unknown function f. What did we build? Okay. Well, if a and b are 0, so 0 is here, that means this closes. The 0 is here, that means that closes. And both of those are open. So I am now connected to power. So at 0, 0, I see a 1. Well, now I know for a fact that I can't, because I just enabled the only way that I can see VCC, right? The only way that my output F can be connected to power is if both of those are on. So I know the other situations are going to be not one. We could potentially end up with a situation where it's neither one nor zero, right? Where I messed up that drawing before, and it could end up in a situation that it was, we don't know what it is because it's not connected to anything. So we want to make sure that the others make sense, right? We could just go 1 0 0 0 if we assumed that I was always right, which we know is a bad assumption, right? I'm not going to always be right. You guys aren't going to be always right. Let's check it. So if A is 1, this one closes. And if B is 0, well, this one's open or closed, but that one's open. So we could draw that as switches, right? Which is to say, well, I said A is my 1. So I have from power, I have a switch that's open. I have a switch that's closed. F comes out. I have a switch that's closed. A switch that's open. This is my circuit. Is there a path that I can take from VCC to ground? That would be a problem, right? Because if I connect power to ground and there is no resistance in between, what is my current? We go from Ohm's law, we say I is equal to V by R. If R goes to 0, I goes to infinity, and I just broke everything, right? It burns up, starts fire, it smells really bad. Don't worry, it'll do that a couple of times throughout. You will, it's fine. You will start fires on your little breadboards. If you see some of the ones that I loan out, a couple of ones, the breadboards that I loan out have like little melty spots on them because of, yeah, because this happens. But anyways, there's no path, right? So if I try and draw a line from ground, it follows here and it's broken. Everything's fine. This is a good circuit. It should never. And so that means that in the case of A is 0, B is 1, A is 0, B is 1, I got 0. Well, it turns out I don't even really have to change this picture the way I drew it for the opposite case, 1 0, right? Because those would just switch. And I've already established that circuit elements in this class are all going to be linear, meaning the order doesn't really matter. I can switch the order of them. And so the same circuit, 0. Now all I have to do is go, what happens of the 1 1 case? Well, on the bottom side, 1 and 1 means they're now both closed. And on the top, they're now both open. Well, I've doubled up the situation where I doubly can't get the VCC. Doesn't really matter. And I can twice as easily maybe get to ground, kind of, but there's no resistance. So it's twice as easy as 0 is still 0. And so I get 0. What did I build? NOR gate. So yeah, right. Your intuition served you well, and that you already kind of understood the relationship between NAND and NOR, that they're going to be opposite. And again, if I wanted to make an OR gate, I have to slap on an inverter to my NOR, and I have 6 gates. This is why we teach the bubble pushing, right? Is because the circuits that you build using NAND or NOR logic are the minimum size circuits. They use the fewest number of transistors by a significant margin, actually. If you're using AND and OR, right, you're using 6 instead of 4 for every transistor. And if you have 100 million transistors in a device and you are 50% bigger, right? 6 is 50% bigger than 4. That's a big difference. And we've already established that they're not quite ideal, which means the gates have a little bit of leakage. That also means it consumes 50% more power-ish, roughly, right? So problems. That's why we convert to NAND or NOR. And then we usually pick either NAND or NOR rather than both just for the scalability, right? We choose the NAND or NOR, the universal gates, because of the size, and then we stick to just one or the other for scalability and affordability. Okay. We can quite easily turn this into a 3-input OR gate, right? I've always done 2, 4, whatever, but sometimes I just draw the 3s. Turns out 3 is fine and easy to make, which is you just extend let's change the way I draw this just a little bit. There we go. I have 3 inputs, A, B, and C. And now, in order to pull up, I need A to be 0, B to be 0, and C to be 0. And on the pull down, I need A or B or C to be 1. And you can go do the analysis, fill out the truth table, and find out that this does in fact not light anything on fire. Cool.
You can do that. Like you could have however many variables you want.
Yes, that's where we're going next. Actually, good question. So what he pointed out is, let's just do it again, right? Let's throw a D here, add another one, and add another one in parallel, and then an E, and then an F, and then a G, right? And I can start doing it infinitely. Well, guess what? It turns out it doesn't quite work that way, because there's magical math that you'll learn later that in order to meet the on condition, right, that I'm saying in certain conditions, we allow that we can pretend that these are digital devices. However, if I have, and this is kind of intuitive, I think, if I'm wrong, let me know, actually. This is. So let's say this is 5 volts and each of these are 1K. And now I have this relationship, so I have Ohm's law, right? And the resistance, each one I throw in series is adding up current, but we've already kind of established that no current ever flows through these things, hopefully. So the current's not really the issue, except for the leakage. So that is what becomes kind of the issue, because this guy, whatever device I plug into, right? Because theoretically, I'm going to come plug into some other device, right? Because I have like a NAND into an OR into the real world or something, right? This guy has some amount of current that he pulls, and that means it throws through here. So it starts creating voltage drops. And in fact, these devices have to have voltage drops in order to be allowed to turn on. And so what happens is that if this is 5 volts and this is 0 volts and these are 1K, then each one of these resistors, the voltage drop over them. So we're just doing plus to minus, right? Plus to minus, plus to minus, plus to minus, plus to minus. Each of these voltage drops is going to be just 1/4 of the 5 volts. Because they're the same device, and I told you they're linear. So if they're the same size, I don't care what the order is. And so what that kind of intuitively ends up implying is that this is 1/4 times 5 volts. And this is 1/4 times 5 volts. 5 volts. 1/4 times 5 volts. And 1/4 times 5 volts. So that if I go up a quarter of 5 volts plus a quarter of 5 volts plus a quarter of 5 volts plus a quarter of 5 volts, I get to 5 volts, right? This is all Ohm's law says in the more complex. If you're in like 1270, you probably already started talking about this. If you're not, it's fine. This isn't going to be on the test. I just want to start establishing that what happens is from the gate to the other two nodes need a specific amount of voltage. And the higher I pile these up, the less voltage I have available. And eventually I have to stop pretending like they're digital devices and they no longer work. So that's my limit, is what is my voltage overhead, right? And so we have this trade-off between the voltage overhead that we have, 5 volts, and well, how small the devices get, right? So if I bring 5 volts down to 1.8 volts, 1.8 volts is smaller than 5 volts. That usually means less power, but maybe it means I can stack fewer devices, right? And you'll go into kind of these design trade-offs and device physics later. I just like you to know where you're kind of going, right? That's all this is for. So there's going to be some limit on how big we can build these, which is why you a lot of times see them. We build a 4-input AND gate out of 3 2-input AND gates because there's a limited amount of voltage overhead that I can use to stack these up. That's why. We're not like torturing you with this arbitrarily. There's real design decision that makes this limit the number of inputs that we're allowed to have on an AND gate. But nothing stops us from imagining that the 4-input AND gate is, that you just have a 4-input AND gate and then you just build it as 2 2s and you abstract it through block diagrams. And it turns out the computer will build the insides for you by the end of this class. So you don't have to think about it too hard, but it's good to know what's happening because you have to understand delays eventually.
So isn't it going to be slower if you add more components to it though? So like when instead of just using a 4-input AND gate, if you use 3 2s, wouldn't that be slower?
Yes, there's more delay the more layers of logic you have. But there's the trade-off of they're actually smaller devices when you do that. So then it goes faster. And I actually don't know where the analysis falls out. And it probably actually depends on process to process. Like it literally might change from company to company where that trade-off falls. Okay. Now there's something else cool that we can do, which is oftentimes, we're gonna have 2 digital systems that talk to each other, right? And like, here's the simple example. I'm gonna have a 3-input gate going to some other circuit that's gonna interact. And we have this cool thing that you're gonna actually run into in 3610, so I teach digital systems. You don't have to take digital systems. Technically, you can take digital systems or power. There's a choice between those two. I recommend digital systems. It's more money and there's more jobs around here. And it's really fun. I think digital stuff is really fun. I didn't when I was a student, actually. I found this awful because I was bad at it. I eventually got good at it. And now it's fun, right? I guess when you're good at things, it's fun. Anyways, in 3610, if you decide to take that, we're going to be interfacing to other devices. And one of the issues is the devices sometimes can pull to either 1 or 0, but not both. They don't have complementary outputs. And what this does for you actually is it kind of prevents it from the receiving device making a 1 and sorry, I've got to back this up. I skipped a part. This is a part what problem when I don't print out my notes, right? Is you're gonna have a device that you're talking to and you only get 2 wires, okay? One of them is ground because you need something to be referenced to, and one of them is signal. And they need to talk to each other back and forth, but there's only 1 wire, okay? So what happens is, let's say one device, it's its turn to talk, and so it's gonna send a 0 or a 1, and the other device is gonna listen, and then it's gonna go, okay, it's my turn to respond, and it's gonna start sending data. The problem is if they try and talk at the same time, they might break. right? If both of them, if one sends a 1 and one sends a 0 and they're talking over each other, if we talk over each other, it gets noisy and we don't understand. That's also true, but in the case of digital logic, they light on fire as well as don't understand, right? Which is problematic. So we have an ability to prevent this from happening. And the ability that we do that is just open drain is what it's called. I just do this. So now what's happening is the output is sending into a gate. The gate has no input current, right? We're going to pretend like that for the moment. And what that means is that this is decoupled or doesn't see the output. We've separated the output from the input because it's got this intermediate stage. This stage can make a 0, but it can't make a 1. Well, if I have a device on the other side, and it also can only make a 0, now they can't break each other. And now we just accept the fact that, well, resistors are big and obnoxious, but sometimes we got to use them. And now in order to make a 1, they just don't make a 0, right? Because it gets pulled up. If I close that NMOS device, then it makes a 0. If I don't close it, it makes a 1. If they both close, they're both 0, nothing breaks. They're not really talking to each other. It's just that it's like if I'm talking to you and you say the same thing at the same time, and if we're perfectly in sync, everybody else can still understand. It just sounds like we're weirdos that synchronize our conversation. That's all that happens. Now it prevents it from breaking. We have this cool architecture called open drain architecture that allows two devices to have what is called an I/O. Sometimes you'll see a dash between it. An in-out port. That port, right? We've talked about ports before in block diagrams. The port on this device is both an input and an output, which is really nice because now I can use only 2 wires, one being ground, one being the signal, in order for 2 devices to talk back to each other, and there's no chance of them breaking. Does this make sense to everyone?
So it can only be, they can only either be open or closed at the same time, like they're in sync.
No. So what happens is, so this is like signal Q, and this is going to be signal Z, let's say. And let's say I build a digital logic. Let's call it an FPGA. If we're going to learn how to build FPGAs, let's say I build one and you build one, and they want to talk, and we only have 2 wires. Well, one of them we're going to share the ground, so we know that the reference is the same. And then we're going to connect this wire. I haven't used F yet. Together, they're plugged together, and one side or the other or both may have pull-up resistors. It doesn't actually turn out to matter very much. Most of the time, it'll be only 1, but it's okay if it's 2. And so then F is a shared signal. It's the conversation that we have. It's a phone line. And so what happens is this one is going to go open is 1. So it's the computer's talking 1s and 0s, right? So it goes 1 0 1 0 1 1 0 1. And then it says now it's your turn, and the other one goes 0 1 or 1 0 0 0 1 0 1 or whatever. And so they just take turns. And what all this does is, if there's a miscommunication, if they fall out of sync, then it doesn't break.
That's because it's a pull up network.
Yeah, because a pull up resistor is servicing both of them, and you're never going to have this because this isn't a Cmos device. It can handle that current flowing through it and be okay. Whereas if instead of this, each side had PMOS devices and tried to talk, and this one says 1, and this one says 0, then the current from VCC to ground, there's no resistor in between, there's no current limiting resistor, the current goes to infinity, and you just broke both devices. Right, not good. So that's where the open drain comes in. We will actually use this in 3610 digital systems to make two things talk to each other. There's a chance we'll get to use it in here. I'm not sure. These labs are already pretty constrained. When we use these devices, you're obviously not going to go draw transistors, right? That would be silly and weird. This is an inverter, right? We know how to build an inverter out of transistors. If I want to signal that my inverter has an open drain output, E, enable. It turns it on, right? Sometimes you'll see it labeled as EN. Sometimes you'll see OE, output enable, right? That's all that's saying. And it turns out we can draw a truth table for this. We're gonna call that A. This I for invert. We draw a truth table. Normally an inverter only has A, right? But in this case, I've added a new input, E, or EN or OE. And in the case of this 0, 1, 0, 1, 0, 0, 1, 1. Well, in the case where I am enabled, it just acts like an inverter on A. 1, 0. It inverts A. But when I'm not enabled, it's not connected. What is it? Well, there's a reason that I chose I on this one rather than like Z, right? I use Z a lot for outputs. Well, it's because there's Z. Now, Z stands for impedance. And when we write Z, what we really mean is high Z, which means high impedance, which means disconnected, right? If things are not connected together, it's high impedance. In an ideal world, that's infinity, but it's not really infinite, right? Electricity can jump from one wire to another. It can arc. The reason it takes a high voltage in order to arc is because the resistance of air is very high. It's very difficult for electricity to flow through air, but it can. And that's what the high Z is saying, is it could, but only if something went catastrophically wrong, basically. That's what high Z means. This is high impedance. Impedance, I guess I probably haven't used that word before. You've heard me use resistance. Impedance is almost the same thing as resistance. It's just that it turns out some circuit components change resistance depending on how fast the electricity wiggles up and down, right? We call that frequency, the frequency with which the electricity rises and falls. That's frequency. The power lines that run all over our country run at 60 hertz, meaning that they go up and down 60 times a second. Well, it turns out some circuit components, resistors don't behave this way, but other circuit components change their resistance when the frequency changes. And so all that means is that we have resistance for when things don't change with frequency. And if they do change with frequency, we say impedance. So resistance is a subset of impedance. That's all it's saying. For the sake of this class, they're essentially interchangeable because we're not going to talk about the complex behaviors of non-linear circuit elements, basically. So we don't have to worry about that yet, but just be aware that's why we're using the word impedance. And technically, we're going to have a different output here that I want you to be aware of. This, for most purposes, I'm okay. This is mostly correct. But I'm not really making a 1, am I? Because that resistor has current flowing through it. Transistors don't, right? Transistors don't have current flowing from source to drain, which means there's no voltage drop over it. When they're closed, there's zero resistance. It's a closed switch. There's no voltage drop over the closed switch. Everything's happy, which means it makes a 1. But in the case of a resistor, if I make a 0, then current flows. And if I make a 1 and there's input leakage on whatever I plug into, then current flows. So that resistor is going to have a voltage drop over it. So that means I'm never going to quite have 1 out there, am I? I'm going to have 0. This is actually very good at making 0. But I'm not going to have 1 because that resistor has a voltage drop. So instead of writing 1, I write high. High is basically 1, right? The incoming digital, the receiving system is going to recognize high is a 1, but it's different because it's not quite all the way to VCC. If we inverted that, right, we could use a PMOS the same way in a pull down resistor. Then we would have, instead of 0, we'd have low because it wouldn't quite reach ground ever. You can have things like, this would actually make a lot of sense. Let's say I had an open drain Nand gate. A lot of times the way that this is going to get drawn is because the open drain part is actually kind of a different circuit a little bit. And so it's just going to use the advantage of saying there's a buffer there, and that buffer is going to have an enable. And now we can ask the question, well, this one, if I make 1 here, then I can connect, right? And so these enables, the output enables, and we can do this a bunch of different ways, actually. There's other ways to build output enables. I'm not gonna cover that quite yet. And so, but maybe N, meaning 1, is turning something on. And maybe the 0 turns something on, right? Allows it to flow through. Okay, in some, because this isn't really how I would build an OE, because like this doesn't know that there's an enable signal, right? I haven't enabled it in any way yet. It turns out these switches are really good. Ta-da. They can function this way. They're pretty good at it. Where if enable comes in and turns this device on, it flows through. If enable is 0, then they're broken and it can't transmit anything. Now I've actually added that signal in there explicitly. But that's all this, I don't think you need to worry about drawing these ever, but that's all this signal is saying, is that I've added a signal that allows it to turn on or not. There are other ways to do it, right? I could basically rebuild this. Let's call this N, which means I have to get rid of this, right? Because otherwise those two are connected and then the same thing, which is in this case would actually be okay. And now if enable is 1, then this could never close, right? So this disables the circuit on this side. Well, then I just kind of need to invert it and so if N is 1, that makes this 0, that turns off this guy, and neither of those paths will work. And if it's 0, that makes this 1, that's closed, either of those paths will now work. Does this make sense? This is also a way of building an enable, is because if the enable is, well, realistically, this is not enable, or in other words, enable dot low, right? This is an active low enable. That means it has this little bubble on it because a 0 turns on this circuit, allow this circuit to work. Does everyone follow that? Maybe?
So you could just put another inverter at the beginning and just be active high.
Yeah, you could throw that in through an inverter and make it active high. Yeah, so it turns out, right, this is why these active low signals are important to know, is because sometimes active low is the easy way to build something. Because if I wanted to turn this into an active high enable using this architecture, I actually need 2 more transistors, right? So depending how you want to build your architectures, it sometimes makes more sense for the enables to be active high or active low. And what it turns out, a kind of nice rule of thumb is, if the signal is part of your data, then it is going to be active high. If it's a part of your control, then it's active low. Not always, but generally that ends up being what happens. And so like this enable is a control signal, right? Data is flowing through, this is making decisions. The enable is a control, it is just saying either you're turned on or you're off. So control tends to be active low because the architecture lends itself to being that way. We'll see the same thing when we get to circuits that have memory, when they remember things. Sorry, making sure I covered everything I need to today. Yeah, so this part of things is open drain. This part of the things called tri-state, right? Because there's 3 states. There's 0, 1, or off, basically. Yeah, so I think that's all I have to cover today. Sorry, this lecture was a little rough. Normally I make it in earlier than I did today, and I remind myself what I'm supposed to talk about in roughly what order, and I didn't make it in early because things happened. I apologize. If you end up confused, I have adjusted my office hours, as you may have seen. I think out of the 30-ish between the 2 classes that I have, I think only 3 people that responded to the poll couldn't make it to the newly adjusted office hours. So I think it's a pretty good one. And at least 2 of those could make it to other of my office hours. So I think I got everybody but 1 person. If you're that 1 person, I'm sorry. That 1 person's availability just happened to be all during my classes, so I couldn't really help. Not a lot that I could do. You guys are free to go if you want. I'm going to spend, I have like 5 minutes. I'm just going to do a couple of problems from homework 1 if anybody just wants to see and kind of watch that. I'll post the answers shortly, so don't feel like you're missing out if you have to go. Make sure that you get homework 2 in, right? And please start homework 3. I promise you, I can't like guarantee it, but realistically, if you do all of the homework and all of the labs, you'll pass my class. If you don't do those things, you won't, right? Because the homework is like 20% of the grade, which means if you don't do the homework, you have to get like A's on all of your exams to pass. That's really hard. So please get your homework in. I want you to succeed, and just the homework is there to help you do that. It's not there to sabotage you. Yes. If you need help, if you get confused, use my office hours. If you can't use my office hours, send me an email. I will help you as best as I can, which is pretty good. I think I'm pretty good at it.
Is it fine if we turned in the lab today?
Yeah, totally fine.
So I forgot.
Yep.
OR gate? I cannot tell.
That is an OR gate.
Okay, and I don't know what was so confusing about it.
Yeah, just look at the input side, and if it's curvy, it's an OR, unless there's the only real one that you'll get confused on in the OR is potentially the difference between OR and XOR.
Yeah.
Right.
The thing that was confusing is like the little thing in the middle. Oh, it like sticks out. I don't even know what that is.
Yeah. And so I steal the images from around the internet because basically every permutation of circuit has already been done. So there's kind of no point to me making it my own. So the one that I want to bring up, oh, sorry, do you have a question or? Yeah.
I'm just curious, how do you replace
It's
with the
OR gate.
expression?
Just looks like a cylinder.
Yes.
I started going backwards.
Have time for office hours after this class, or you have something?
I'm
Hey, let me do this one and then I'll help you. Is your class here? Great. Okay, the one that I want to do from number one is the question number 3, which asks about analog and digital components, where it says characterize the following signals as either analog or digital. It looked like when I clicked through, I haven't finished grading them yet. You'll see the grades popping up soon. The voltage on a microphone is analog. Most of you got that right. The daily closing price of GE stock is the one that I saw most often wrong, which is that is actually digital, because they don't run out to infinite numbers, right? GE stock is going to be like, I don't know what they're sitting at right now, $50 point something, 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 stop. If that went on forever, it would be analog, but it doesn't, because at some point it ends, it's digital. It needs to be fully continuous. It needs to have no rounding, but they do round, right? Like dollars are not continuous because we stop at pennies. We don't have anything. Those are currency is digital. We can kind of like take half pennies in Bitcoin, but right, eventually it stops dividing down. The green signal of traffic light. I stole this question. I don't like this question. Green signal. Most of you got this, what I would consider right, which is digital. But if you went and said analog, guess what? I don't think you're really wrong either, because the right way to phrase this is a traffic light digital or analog? The traffic light is clearly digital, right? Because it has 3 different things that it can be: red, yellow, green. However, the green light specifically is kind of analog because light is analog. And so it's kind of obscure. So if you got that one wrong, I'm not gonna mark points down because really either answer is okay. And I think, I don't know if I've seen anyone get this one wrong. The temperature in a room is analog, right? We can measure it digitally, but the temperature itself is continuous. Let's do just one of these Venn diagrams. I think that was really good was the A or BC. So the A, when I see something on its own in the OR, means I just get to fill in that whole circle, right? And then the OR, I just look for where the B and C is, which is this overlap here. That fills in. That's all the Venn diagram does. The hardest one is the F. Is not A and B and C, which we have to go and start figuring out where each of these kind of regions are, which is we're in the not A region, which means this whole thing is not part of it, right? We are not A. Then I have to be somewhere within inside of B and somewhere within inside of C. And so the only place that is not inside of A, is inside of B, and is inside of C is that area. Make sense? Cool. I'll post the rest of the answers as soon as I'm done grading and stuff, and I'll do the same thing for ensuing homeworks. This recording will get posted, even though it's terrible and I'm embarrassed about it.